Welcome to the second part of Lecture 18 for Chemistry 312, Radiochemistry. This lecture is on applications of nuclear materials. Part 2 of the lecture on the application of nuclear materials will focus on radiopharmaceuticals. We'll discuss and explore diagnostic radiopharmaceuticals, those that emit photons and used to understand function in the body. We'll also discuss therapeutic radiopharmaceuticals, those isotopes that emit Auger electrons, beta particles or alpha particles. These particles are used to kill cancer cells, so provide a therapy. And then within these two, we should remember there's also theragnostic, a combination of isotopes that emit a particle and a photon that can be used for both diagnostic and therapy. Medical isotopes are also a large area of application of nuclear material. Again, as a review, there's two routes for producing medical isotopes: neutron reactions, where uranium is fissioned. One can utilize the fission products, or the neutrons coming from the fission process can be added to a target, reacted with a target, and then that target is used to obtain the product of interest. From neutron reactions, products tend to be neutron rich, and they tend to decay through either beta decay or alpha decay. Accelerators are often used to produce positron emitters, and they can also be used to produce Auger emission type of isotopes. And again, these accelerators use a reaction where a target is interacted with a beam. The beam can be any sort of charged particle. Often some details are necessary within your target, such as cooling, either water or gas cooling, since these nuclear reactions tend to be energetic and form heat. A specific example for the production of medical isotopes is provided here for astatine-211. This reaction is using a bismuth 209 target, helium projectile, 2N reaction to make the target radionuclide. This radionuclide, the astatine-211, is then introduced to a monoclonal antibody. It's covalently bonded to this monoclonal antibody using the chemistry of astatine, and this production is performed at the UW Medical Cyclotron facility. The isotope production information is provided here, as using examples of some information discussed earlier in the course. These are some cross sections as a function of energy, and we see the cross section for this reaction goes up to about a barn for the bismuth 209. The alpha 2N reaction peaks at around 30 MeV, while the 3N reaction, as we discussed in some earlier lectures, would peak at a higher energy, and we see here it's at 40 MeV, and the cross section again is slightly over a barn. So one would surmise from this data that if one wanted to preferentially produce the astatine-211, the preferred cross section would be on the order of 30 MeV. You see your cross section for the 3N reaction is very low, and it peaks for the 2N reaction. When astatine is bonded to the monoclonal antibody, the antibody can then travel to a cancer during the decay of the astatine, which has a 7.2-hour half-life. Decays by two routes: electron capture to polonium, very short-lived polonium isotope, half a second, which then decays to stable lead-207. This decays in alpha, so you have electron capture followed by an alpha, or 42% of the time you get the astatine-211 decaying to bismuth-207, and that bismuth-207 has a half-life of 38 years. So nominally this bismuth-207 would be excreted by the body. Some of the data on the therapeutic properties of the alpha particle from the astatine. The mean linear energy transfer is provided here, which is about 100 keV per micron, and the tissue range is on the order of 55 to 70 micron. A number of other isotopes can be produced at the UW Medical Cyclotron facility. The cyclotron has the capability of accelerating different particles, alpha particles as we discussed for the astatine-211. One can also produce tin isotopes for medical applications. This is the energy range and the beam current. For deuterium reactions, again, the energy range is from 13 to 24 MeV, and different isotopes can be produced, including neptunium-236, rhenium-186, and at some higher energies for proton, one can actually perform therapy with the proton itself, produce fast neutrons from the proton reaction, use that as a therapeutic tool, or use this route as production of technetium-99M. And again, the technetium and the rhenium are both group 7 elements and will have similar chemistries in radiopharmaceutical applications. For medical isotopes, the decay modes are important for their applications. Alpha decay and beta decay can deposit high amounts of energy in a cell. An alpha will travel about 1 cell length. Beta particles will travel almost 10 cell lengths. So one can evaluate this as a route of killing cells. And if one evaluates this, the linear energy transfer is much higher in an alpha particle. All that energy can be deposited in 1 cell, where for a beta particle one can estimate on the order of 1/10 of the energy winds up being deposited in any given cell. However, alpha particles and beta particles can be used in therapy where they can kill tumor cells. Auger electrons, which we'll describe, can also have therapeutic capabilities. Gamma decay and positron decay are generally used for imaging. Both these result in photon emissions. The photons are detected external to the body, which can be used to image activities in the body, either image the location of a cancer or image the physiological behavior of a system. In the positron, the 2 photons are produced through a matter-antimatter interaction, and that is actually useful in developing high-resolution images. An overview of positron decay is shown here. The key is that there's a positron-electron interaction. This annihilates the antimatter positron with the matter electron. As shown here, you create 2 gamma particles, or 2 photons, that are at 511 keV. That's the mass of each one has a mass of the positron and a mass of the electron, and they're 180 degrees from each other. This allows a specific energy to be evaluated, the 511 keV, that's indicative of the positron decay. And the fact that they're 180 degrees from each other means that a coincidence system can be set up, and when the gamma particles, when the photons are detected in an array 180 degrees from each other, working backwards will give you the location where the positron decayed, and this can be used for high detailed imaging. Photons are generally emitted due to gamma decay, and this could be either from a metastable nucleus, such as technetium-99M, where that relatively long-lived excited nuclear state de-excites by emission of a photon, or from the decay either through alpha or beta to an excited daughter state, and then the de-excitation of that daughter state through the emission of a photon. X-rays are also possible route for emission of photons, where an electron from a lower energy level is removed. The electrons from higher levels occupy that lower level, and the resulting vacancy is de-excited with the photon emission. Auger electrons are in very ways similar to X-ray emission, except that as opposed to emitting of a photon, one of the outer electrons are emitted with the energy that's consistent with the transition from the electron moving from a high energy state to a lower energy state, and then the outer electrons are then emitted. So for radiopharmaceutical studies, what one does is exploit the chemical species and coordination chemistry of the radionuclide to develop compounds. Again, the center radionuclide, for this case an example of technetium-99m, can either decay by gamma, in the case of technetium-99m, which is useful for imaging, or alpha, beta, or Auger electron for therapy. And we're going to do our first example with technetium-99m, which is produced from a molybdenum-99 generator. The reason we're going to focus on technetium-99m is it is the workhorse of radiopharmaceuticals, where about 80% of all radiopharmaceutical applications use technetium-99m. And also this compound, its utilization is highly linked with technetium coordination chemistry. And an example is shown here, where one can make a technetium core. This technetium carbonyl can then be placed into a number of different ligand systems. Each of these ligands has a different biological behavior that can be used to image different aspects of biological systems. The technetium in this form is the technetium carbonyl, goes along with the ligand, and as it decays, it images the physiological behavior that is based upon the ligand behavior. So again, a radiopharmaceutical combines this isotope that we've talked about how we produce with a physiological behavior based upon a ligand system that it can be attached to. We'll also discuss some simpler examples where the ligands are nothing more than chlorides. Technetium-99m has a number of limited production facilities. Shown here are basically the worldwide production facilities for technetium-99m, which is produced through the fission of uranium in reactors. This line here shows the fission yield for molybdenum-99. It's a very high fission yield. What occurs is that the uranium is placed into a neutron flux around 6% of the time. During the fission process, it forms this molybdenum-99. Upon the end of the radiation, the target can be dissolved. The molybdenum forms an anionic species as shown here, and then it can be separated, purified, added to a column, and then it decays to technetium as shown here. It has the molybdenum-99 has a 66-hour half-life. It decays to the excited state of technetium, the technetium-99m, which has a 6.01-hour half-life, and then that technetium-99m decays to the technetium-99 ground state through the emission of a photon at 140.6 keV. So these generator systems, which are used to produce technetium-99m, are commercially available, and they're fundamentally aluminum. The whole process runs on aluminum chromatography, where after the separation, the molybdenum in the form of molybdate is sorbed to the column. Upon the decay of the molybdenum-99m to the protectatate, the protectatate is less strongly bound to this aluminum column since it is monoanionic. You can elute the protectatate from the column with normal saline solution, and as it comes out, the saline contains the technetium. Here shown a growth and decay curve for molybdenum 99 and technetium 99M. You see that the bulk of the technetium activity, shown here in blue, is generated within the first week of the generator system. So once the molybdenum is sorbed onto a generator, the generator can then be shipped to a hospital. The technetium is eluted. In the saline solution, it's added to a kit with an organic specific radiopharmaceutical, and that compound is then introduced into the patient to achieve some physiological imaging. An example of an imaging agent is shown here, Cardiolite. The compound of Cardiolite is shown here. As you can see, it's a cation. There's been 40 million applications of Cardiolite since the 1990s. This cation accumulates in myocardial membrane, and what this is used to do is to see how well heart muscle behaves, and it's used in cardiac stress test. So one can compare the uptake and behavior of the mitochondria, or the energy for a muscle is produced. You can see how well the muscle is behaving in a rest and exercise mode for the heart, and this is used medically to determine the health of the heart. Ceretec is another example of a technetium compound. This has the property of crossing the blood-brain barrier, and it can be used to image the function of the brain. So, for instance, it can be used to evaluate the presence of dementia. If strokes have influenced brain activity, so one can evaluate if the technetium is getting into all parts of the brain, and if not, it could be an issue that strokes have prevented blood flow to the brain, and also arteries that feed the brain, if there are any clogging or clotting issues with those arteries. Other ligands that have been evaluated with technetium include this ATSM ligand. The technetium would sit right here in this metal, in the ligand center, forming a metal ligand complex, and this is useful for imaging areas of low oxygen content in cells. So this is a way of imaging those areas of potentially damaged organs that are not able to repair themselves due to low oxygen levels. Other ligands, an example, a key ligand shown here called DOTA. Here's the structure of DOTA. Here's the chemical name of DOTA. DOTA is a widely used compound for coordinating metal ions. And then once coordinated, this ligand can be either introduced as itself as a radiopharmaceutical or attached to something such as a monoclonal antibody, which will have a response to go after certain tumors within the body. So for instance, if one has a monoclonal antibody for a specific tumor, one can tether a DOTA to the monoclonal antibody, incorporate a metal ion such as lutetium-177, actinium-225, that would be transported to the tumor site and then during the decay cause tumor cell death. Another isotope that's commonly used in therapy is iodine-131, and this is simply based upon the fact that the thyroid takes up iodine effectively. The iodine is introduced as a sodium iodide compound. There's no ligand needed. One just needs to limit the amount of iodine that's taken up prior to therapy, so that the iodine, so that the thyroid is not saturated with iodine. Now, iodine-131 is a major fission product. However, one cannot use fission iodine due to the presence of other isotopes, including iodine-129, which is a very long-lived isotope. Some of the data for iodine is shown here. It's a half-life of 8 days, decays down to xenon, also has gammas associated with it. These gammas are unfortunately responsible for external doses from the patients. However, they can also be used to image the uptake of the iodine 131 by the thyroid. Since fission product iodine cannot be used, neutron irradiation of tellurium is used to produce the iodine. Iodine is the daughter from the beta decay of tellurium 131, which is 25-minute half-life. So tellurium, elemental tellurium, which contains tellurium 130, is irradiated. That produces your tellurium 131. That decays with a 25-minute half-life to iodine 131. And the iodine can be separated from the tellurium either by ion exchange or distillation and then subsequent dissolution of the iodine. Similar to iodine 131, radium dichloride is a therapeutic agent. Radium 223 is the isotope that's used for this therapy. It has a half-life of 11.4 days, decaying to radon 119. The radium, this very simple compound, is used since radium is divalent, as is calcium. It'll go to the bone. So this compound, commercially called Xofigo, is used to treat pain associated with cancers of the bone, shown here. So the alpha particle is a very low range. The cancerous bone material is growing rapidly, uptakes the introduced radium 223, and upon the decay of the radium with the alpha of almost 6 MeV, induces cell death of the cancer. That has a palliative effect and reduction of pain. Radium 226 is produced from neutron radiation. The radium 223 is produced from the neutron irradiation of radium 226. Radium 226 obviously will also go to the bone. However, its half-life is 1,600 years, so the specific activity is not nearly as high as the radium 223. And this is the decay. This is the capture, making radium 227, which undergoes beta decay to actinium 227, beta decay to thorium 227, and then alpha decay to radium 223. This is the first alpha-emitting radiopharmaceutical that's been approved by the U.S. Food and Drug Administration in an unsealed route. Other reactor-produced isotopes are shown here. Bismuth-213, an alpha emitter, is also used for targeted alpha therapy. Dysprosium-165 is used for synovectomy treatment of arthritis. So as a aggregate or as a colloid, it can go into the joints of arthritis and treat the pain. Erbium-169 has similar properties. Iodide-131, as we discussed, is used particularly for thyroid. Lead-212 is used in targeted alpha therapy. And lutetium-177, which is chemically similar to compounds such as actinium-225 or the other lanthanides, can be used as a therapy agent since it emits beta particles, but also has enough gamma for imaging while one does the beta treatment. So this isotope has this dual property where the gamma decay from its beta emission can be used to image its behavior. Some more reactor-produced isotopes, including rhenium-186. Rhenium is chemically similar to technetium, so those radiopharmaceuticals that are developed for technetium imaging can use rhenium as a therapeutic agent. Samarium-153 is also a lanthanide that has been explored for relieving pain in cancers and bones, similar to the Xofigo. And then an isotope of xenon is also used for pulmonary or lung ventilation studies. And yttrium-90 is being explored for liver cancer treatments. An example of a positron emitter is fluorine 18, which is one of the largest used positron emitting isotopes. An example here is combining the fluorine 18 onto glucose to evaluate brain behavior. The fluorine is cyclotron produced from the reaction of oxygen 18 with a proton-neutron reaction with water as a target. Neon gas can also be hit with deuterium and alpha product for the fluorine 18. The fluorine is separated from the target and then chemically reacted onto compounds, and in this case glucose. The half-life of this fluorine isotope is a little over 100 minutes, with a large percentage decaying through positron decay. And the decay scheme is shown here, where the fluorine 18 decays through positron or electron capture to oxygen 18. And one can evaluate the behavior through controlled experiments where the brain can be imaged that shows the presence, in this case, of Alzheimer's disease. A list of cyclotron produced isotopes is provided here. A number, in addition to fluorine 18, there's oxygen, nitrogen, and carbon isotopes that are also used for positron emitters. There's germanium 68 that's used as a parent to generate gallium 68, and gallium 68 is a positron emitter. Krypton 81 is also produced in a similar route from rubidium 81. The krypton gas can again yield functional images of the lung, and then thallium 201 can be used to diagnose coronary disease. It's commonly used as a substitute for technetium in stress tests. So, reviewing this lecture, a combination of chemistry and nuclear reaction can be applied to isotope utilization. A number of nuclear reactions are possible, both neutron-based reactions and accelerator particle-based reactions. One can also isolate particles from isotopes from natural decay series. For instance, we didn't discuss in detail, but bismuth-212, which is a natural decay series, has the same sort of targeted alpha therapy properties as bismuth-213 and can be used as radiopharmaceutical. The interaction of the particles can be useful in evaluating material, the presence of water, the role of particles such as explosives or smoke, and also these particle interactions can be used to generate heat from the isotope itself, as an example with the plutonium-238 as a heat source and a thermoelectric generator for space travel. Radionuclides can be used for therapeutic and diagnostic applications. The radionuclide can be free or bound to a ligand. Often it's bound to a ligand, but we've discussed two cases of iodine and radium where it's fundamentally free. And this research that's ongoing can be used for a number of different radiopharmaceuticals. We showed a list of potential radiopharmaceuticals that can be used. However, the ones that we discussed in the lecture, iodine, technetium, fluorine, are the bulk of the radiopharmaceutical applications. And examples of questions you should be able to answer from this lecture. What nuclear reaction is used to make iodine-131 for therapy? Well, iodine-131 is a prominent fission product. However, other iodine isotopes also are produced through fission that are not suitable. So iodine-131 is produced from neutron capture on tellurium, particularly tellurium-130. The N-gamma reaction yields tellurium-131, which then beta decays to iodine-131. And 34% of tellurium is the 130 isotope. So this is actually a very reasonable route for the production of iodine-131. So what's this role of americium-241 in a smoke detector? The americium-241 provides the alpha sources, the alpha particles that ionize, that result in ionization. Generally, when there's no smoke present, the alpha particles are ionizing air. This creates a low current that is measured in the ionization chamber. When smoke enters the ionization chamber, this current is decreased since some of the ionized particles will absorb to the smoke, and this indicates that smoke is present with the resulting alarm from the smoke detector. What radium isotope is used in Xofigo, the allowed radium-based radiopharmaceutical, and that is radium-223. Its half-life is 11.4 days. That's a suitably short half-life as opposed to radium-226 with a half-life of 1,600 years. It wouldn't have the same specific activity. And our technetium-99M radiopharmaceuticals, therapeutic or diagnostic. Technetium-99M decays by gamma emission, so they are diagnostic. Now, rhenium-186 can be used in conjunction or in the ligands that bind technetium. The rhenium and technetium chemistry is similar enough where this can be used as a route for a therapeutic treatment that can be imaged through technetium.
When you have completed this lecture, please comment on the blog and respond to the Lecture 18 quiz. The lecture outcomes are described here. One should be able to understand and discuss techniques for isotope production. This includes the use of accelerators for the production of neutron-deficient isotopes, those that decay by positron or electron capture emission, the production of fission products for neutron-rich isotopes. An example of this is molybdenum-99. Isotopes that are produced from neutron capture. This can include californium-252 as an example. And compounds that are used for neutron-emitting systems, such as an alpha emitter with beryllium. You should be able to discuss and describe the use and application of isotopes. Examples are provided in the lecture for detection of compounds and energy sources from radioisotope generators. And you should be able to describe in some detail medical isotopes, including the properties for diagnostic and therapeutic applications.